This is Charles Underwood. I'm covering topic 50, Geology of Dam Construction and Tunnel Construction, for Physical Geology 1403 for Professor Ravindra Nandigam for spring 2025. First is the table of contents. I will be covering over in this presentation the challenges of dam and tunnel construction caused by geology. First, I will be touching on dam problems. Second, I will be covering over the innovations in dam construction. Third, I will be covering over tunnel problems. Fourth, I will be covering over the innovations in tunnel construction. And then finally, my conclusion and my references. Up first is dam problems. Many issues can arise from the construction of a dam, some that are more obvious like stagnant water, flooding of local habitats, and the like, but the containment of water can introduce unforeseen geological issues. Water is heavy. It's about 8 pounds per gallon. Many of the reservoirs contain millions of gallons of water capacity, if not more. This weight disfigures the crust of the earth, as highlighted in this quote from Penn State University's Earthquake and Structural Failures module by Michael Arthur et al. Impoundment of water behind major dams changes the distribution of stress in the Earth's crust, and in combination with downward percolation of impounded water can trigger seismicity. For the most part, this phenomenon is restricted to increased numbers of small magnitude, less than 3.5, earthquakes triggered by the increased load of millions of cubic meters of water, associated warping or flexure of the crust, and diffusion of water pressure from the reservoir along fractures and fault lines. This highlights an interesting occurrence that, at least for myself, I didn't take into account with geologic activity. This is only one issue of the dozen other potential problems, so I will highlight one other, that of reservoir leach into groundwater. The point of a dam, obviously, is to trap water. Without proper soil composition, this is not possible. As such, a general rule of thumb, the underlying soil content must be at least 20% clay. As you can see here on the presentation, there is a photograph of the clay sand silt triangle, and it shows you the more optimal composition of soils for the underlayment of a dam. For earthen dams, depending on underlying soil and available earth, modifications to the dam such as a clay core may be necessary to combat seepage, also seen in the figure on screen. Moving on to tunnels. Tunnel boring, while not having to deal with underground stresses that can cause seismic activity like dams storing water, because you're not really going to introduce more weight through a tunnel construction, you will have different issues that are caused by the geological structure of a tunnel. A quote from Jared Coleman et al. Quickly emphasizes this, stating that it is difficult for the machines to cut through weathered, sheared, and highly jointed rock, showing how even small changes and imperfections in the rock itself can change the timeline of a boring project if not sufficiently planned for alongside significant testing. Without the work of geologists and surveyors, many projects wouldn't get out of the development phase, much less into the actual construction of the tunnel. Jim St. Marie comments further on the problem facing boring projects due to the changes in rock. He states, even solid rock contains often innumerable cracks, faults, folds, and discontinuities, the activation of which can any of which may become a trigger to a collapse of the tunnel. The design and construction of a tunnel must account for the mechanical properties of the surrounding rock, which includes not only the aforementioned cracks and discontinuities, but also the weathering and deterioration of the rock, the number and type of layers in the rock, the strike and dip of these layers, underground water level, overburden, and the list goes on. These are all concepts that we have touched on at some point in this semester, from the strike and dip of a fault plane to the groundwater level of an area to the weathering of different rocks through chemical and mechanical means. All isn't doom and gloom, however, as there have been significant advancements throughout the millennia of tunnel construction by humans. One such example of early advancement comes from Sir Mark Isambard Brunel, who made the original Thames Tunnel in 1825. Jared Coleman et al. States about Sir Brunel, Brunel is said to have been inspired in his design by the shell of the shipworm, whose efficiency at boring through submerged timber he observed while working in a shipyard. This design has been improved on significantly with now even the type of boring machine depending on the need of the soil type being excavated, the temperature of the region, and more. The two predominant machines are used are open and closed face shielded machines, with the former being used with stable soils, whereas the latter is being used for less dense and flowing soils like sand. In conclusion, advancements in the fields of geology as well in construction methods have allowed more advanced and better constructed dams and tunnels to be made across the globe. In the modern era, consideration for environmental impacts of these large structures can be just as important in the placement of the infrastructure. While the need for larger infrastructure such as this is lessened in the United States, many developing nations can take advantage of the economic and energy benefits granted by strategic placement of dams for hydroelectric power and more direct transit lines with tunnels for rail and road. My references for this, as shown on screen. And that is all. Thank you.